The hypothesis of the ancient Big Bang is widely accepted by scientists as the primary explanation for the origins of the universe, including the creation of stars, planets, and life itself, including us. Despite its unusual name, the term Big Bang aptly captures the magnitude of the event. Initially, the universe was a dense collection of particles squeezed into a space smaller than a pinhead. From this point, a colossal explosion known as the Big Bang occurred. This event marked the beginning of a process that unfolded over billions of years. However, despite the continued popularity of the Big Bang theory, new scientific data has increasingly tested its predictions. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory to date, scientists hoped its observations would support the Big Bang theory. Remarkably, within just 1 year of its mission, the telescope has amazed experts with its groundbreaking capabilities, providing unprecedented views into the universe's early stages. The JWST's findings have revealed galaxies so ancient that they could challenge how we understand the universe's origins. One particularly notable discovery came when astronomer Rohan Natu, examining early images from the JWST, accidentally discovered a galaxy that astonished everyone. This galaxy, named Glass Z13, appeared extraordinarily massive and was traced back to just a few 100 million years after the Big Bang, making it older than any galaxy previously observed. Natu's excitement was palpable as he shared the discovery, describing it as beyond anything cosmologists had ever imagined. The JWST was designed to observe the universe's most distant and earliest galaxies, particularly from a period known as the Cosmic Dawn, which is shrouded in mystery. This era marks the formation of the first stars and galaxies, and by studying these distant systems, scientists aim to better understand fundamental cosmic processes such as the influence of dark matter and dark energy. Initial expectations for the telescope's discoveries were modest, with hopes of finding only a few faint, distant galaxies. However, reality far exceeded these projections, as the telescope's images revealed galaxies of remarkable size and complexity, challenging existing models and sparking intense debate. As researchers continue to analyze the data from the JWST, the implications of these discoveries could be profound, opening a new era of cosmological understanding. The telescope's astonishing revelations offer a tantalizing glimpse into the universe's past, propelling humanity's quest to uncover the mysteries of existence. The sight of such massive and luminous early galaxies has sent both scientists and enthusiasts into a frenzy, eager to comprehend these strange and unexpected findings. Could these unexpectedly large and bright early galaxies be the result of anomalies in the telescope's initial observations, or could they be part of a larger, more complex cosmic narrative? If the latter is true, these galaxies might be the first signs that the universe is far stranger and more intricate than previously thought. The fundamental question is how we would interpret the emergence of the universe we know today from the chaotic beginnings of the Big Bang. The early discoveries from the James Webb Space Telescope have the potential to reshape our understanding of the universe's origins. These revelations concern not just distant galaxies, but also our own existence in the vast cosmos. As Mark McCarran, a senior science advisor at the European Space Agency, who is involved with the JWST, remarked, "You build these machines not to confirm the perspective but to break it. You just don't know how it will break." The JWST's exploration of the earliest galaxies has its roots in a vision that goes back decades. In 1985, before the Hubble Space Telescope was even launched, the Space Telescope Science Institute began considering what might come after Hubble. Initially, there was some resistance to focusing on the next-generation telescope, but Ricardo Juan, then the director of the institute, was determined. In collaboration with a small team, he began drafting concepts that would eventually lead to the creation of what became the James Webb Space Telescope. The team recognized that while Hubble would remain iconic, its capabilities would be limited by its ability to observe only visible light. In contrast, the JWST would focus on infrared light, enabling it to peer deeper into the universe than ever before. The necessity for such a telescope became even clearer in December 1995 when Hubble captured the Deep Field image, revealing thousands of distant galaxies extending over 12 billion years into the past. This discovery showed that the universe was far more vast and complex than anyone had imagined, underscoring the need for a telescope capable of seeing even further. After more than 20 years of development and a cost of about $1 billion, the JWST finally launched on Christmas Day 2021. The telescope underwent extensive testing before reaching its final orbit, and by July 2022, it was ready to begin its first full year of scientific observations. Known as Cycle 1, the mission included high-impact programs designed to probe the universe's deepest secrets. As astronomers eagerly analyzed the telescope's data, they discovered that the universe was more intricate and mysterious than previously thought, reshaping our understanding of its earliest moments. The JWST's observations are set to lead us into a new age of cosmic exploration, offering new insights into the origins of the universe and our place within it. The James Webb Space Telescope, JWST, has ushered in a new era of exploration and discovery, challenging our understanding of the universe's origins and evolution. Its unprecedented ability to peer into the distant cosmos has unveiled remarkable phenomena that defy traditional models, sparking debate and necessitating a rethinking of current theories. One of the most intriguing aspects of JWST's findings is its potential support for the MZ model, proposed by Imprint McCarran, which suggests the existence of dark matter. However, not all cosmologists are convinced of its validity, and there are alternative interpretations. For instance, it's possible that early universes may have lacked the buildup of matter, which could explain their extraordinary appearance and mass calculations. Some researchers like Charlotte Brickley and her team have proposed that JWST might be observing the most energetic galaxies from the early universe, suggesting simpler conditions for star formation during that time. David Spergel supports this idea, indicating that higher gas pressures and temperatures in the early universe, possibly influenced by initial gravitational fields, could have led to the more efficient formation of massive stars. The swift publication of JWST's initial findings reflects a shift toward rapid peer review through platforms like A14 on social media, which has accelerated the dissemination of discoveries. However, concerns about the rush to conclusions before thorough peer review and potential recalibrations remain, as these early results may not be definitive. Despite these uncertainties, the sheer volume of high redshift galaxies observed by JWST suggests that the early universe may differ from prior expectations. Experts like Fin Lin have expressed confidence in the authenticity of JWST's data, noting that the likelihood of cosmologists abandoning these discoveries is minimal. Researchers are now racing to align subsequent insights with these initial observations, and Nancy Levinson is currently evaluating around 12 proposals from different teams, seeking additional JWST observation time to study promising high redshift galaxies. Given the significance of these early discoveries, confirming them is critical. One proposed initiative, led by the Universe Web Project, aims to expand the search for early galaxies by scanning a broader area of the sky. Their efforts could help identify additional ancient galaxies and provide evidence for the first proto-universes, possibly using the death of early stars or supernovae as markers. Some studies suggest that JWST could detect galaxies at a redshift of 26, just a few 100 million years after the Big Bang. Discovering even a small group of such galaxies would be a remarkable achievement. As Natu explains, astronomers are not misinterpreting their observations. JWST has ushered in a new era of science, and despite its challenges, the rapid exchange of new data has reinvigorated the scientific community, fueling enthusiasm for the next phase of research. JWST's discoveries are not just reshaping cosmology but also inspiring the academic community to reconsider how we interpret the earliest moments of the universe. The importance of validating these findings cannot be overstated, as they could provide crucial insights into the universe's formation. The drive to uncover more, fueled by curiosity and discovery, is likely to continue shaping the field of cosmology for years to come. In conclusion, the James Webb Space Telescope has revolutionized our approach to understanding the cosmos. Its unprecedented observations of galaxies formed shortly after the Big Bang have sparked both excitement and debate, prompting a re-evaluation of established theories and the development of new ones. From the mysteries of dark matter to the evolution of early star systems, JWST's discoveries have profound implications for our understanding of the universe's history. As JWST continues its mission, Researchers eagerly await what new revelations lie ahead, bringing us ever closer to unraveling the fundamental questions of existence and our place in the vast expanse of the universe. For vast hours, scientists have been sifting through different patches of the sky, searching for distant galaxies in the early universe. Initially, they anticipated only modest discoveries, such as a more detailed version of the Hubble Deep Field. However, they were in for a surprise. Stephen Lin from the University of Texas at Austin, leading the SE project, explained that extremely distant galaxies were expected to emerge only after multiple data cycles from various projects. Yet, to the astonishment of cosmologists, these galaxies appeared much sooner than expected. Previously, the record for the most distant known galaxy was held by GN-Z11, observed in 2015, with a redshift of 11. Redshift measures the stretching of light due to the expansion of the universe, with higher values indicating greater distance. However, from the first observations of the glass galaxies, two independent teams, including one led by Rohan Natu, identified galaxy Z13 with a redshift of 13, pushing the timeline of galaxy formation back even further. Experts relied on improved redshift evaluation methods based on brightness estimates, rather than more time-consuming direct measurements. Despite being simpler, these techniques revealed unexpectedly bright and massive galaxies, some potentially comparable to a supermassive galaxy, rivaling the size of the Milky Way. These discoveries suggested that these galaxies were billions of years older than expected. The surprises didn't end there. In the days that followed, other galaxies from the same observations, including those from Sears and Glass, appeared with redshift values as high as 20. This indicated that they existed only a short time after the Big Bang. These galaxies displayed spiral-like structures, which were previously thought to be impossible in such early cosmic epochs. Further, another team found evidence of smooth, large-scale galaxies with a redshift of 10, forming less than 500 million years after the Big Bang. This rapid formation of such massive galaxies challenges the assumptions of the standard cosmological model, lambda cold dark matter, lambda CDM. To understand this anomaly, a brief look back at the early universe is necessary. In the moments following the Big Bang, the universe was a hot, dense soup of early-stage particles. Over time, as the universe expanded and cooled, helium and other light elements formed, leading to the creation of the first atoms around 400,000 years later. About 100 million years after the Big Bang, conditions became favorable for the formation of the first stars, composed mainly of hydrogen and helium. These early stars were larger and more luminous than those we see today, and they eventually clustered into protogalaxies, held together by the gravitational pull of dark matter. However, the discoveries made by the James Webb Space Telescope, JWST, challenged this established model, revealing massive galaxies much earlier than expected. Stacy McSeor from Case Western Reserve University noted the surprising absence of smaller protogalactic structures, suggesting that some of the observed galaxies might be closer than previously thought but hidden by dust, making them appear dimmer and farther away. These revelations raise significant questions about the early stages of the universe, underscoring the need for further exploration and refinement of cosmological models. Follow-up observations of Glass Z13 in August 2022 using the Atacama Large Millimeter Array ALMA in Chile cast doubt on the initial findings. Despite using brightness-based techniques, ALMA did not detect the expected levels of buildup associated with Glass Z13, as reported by Tom B. from Goya University, who led the analysis. This suggests that low redshift intruders may be excluded, but ALMA's efforts to confirm the existence of this galaxy in other ways were inconclusive. This highlights the challenges of validating findings based solely on JWST data. Rohan Natu, one of the scientists involved in the research, pointed out the uncertainty surrounding these results. He noted that the good news is that nothing definitive has been proven yet, while the bad news is that JWST cannot independently verify its own discoveries. The most concerning possibility is that the standard lambda CDM cosmological model might require revision. Michael Bohan Cullen, a cosmologist, stressed the magnitude of this potential shift in understanding, stating that these results are highly surprising and difficult to reconcile with our current cosmological framework. Such findings could signal a profound upheaval in our understanding of the universe's origins.